All right, so this is just to show the other colleagues here at Evergreen what I came up with in terms of the stellar evolution in star clusters. All right, so I went out and bought these beads over here. There were many, many more, of course, but I wanted to pull out the ones that are appropriately the right color for stars. And so these beads are representing the different color schemes associated with the different temperatures. The type O stars would be the deep blue color. The A stars are the light blue. And then A stars would be the beads here, the white beads that happen to have a little filler on the inside. Oops, I didn't pick the wrong one. Here, see the filler with it. There's a little bit of pom-pom or something in the center there that I sort of stuffed in there to distinguish it from the other white stars. The other white stars that don't have the filling, the other beads there, that would be F stars. The G stars would be the yellow beads, and then K would be the orange, and then M would be the red stars there. There's more red beads in here than anything else. But what I had the students do was just pick out, from this, without any explanation, just pick out two different colored beads. So for example, this one here and this one here. And I put up sort of a stats sheet. Now, what do I do with those? They're over here. Sheets that sort of approximate what the lifespan of these stars are supposed to do. And I still have to sort of refine this information, of course, but just to get started with this, the type A stars, the white beads with a filled center, main sequence lifetime, they start, well, from the beginning of the collapse of the molecular cloud that forms the stars in the molecular cloud. As the type O stars, which are the hottest, the biggest stars, come together, after that point, about 4 million years after that point, that's when the gases associated with the type A stars start coming together to form, main sequence stars. And so I wrote down around 4 million years because of that. And they stick around on the main sequence for quite some time. According to some of the models that I saw online, they stick around for about 300 million years. And so that's when they leave the main sequence around that point, according to the model that I was using online. And then they become red giant stars. And so I write down red giant at 300 million years. And I made a guess here. I don't know exactly if this is the number here for this, but I said somewhere on the order of 10 million years is how long it stays in the red giant phase. Then it becomes a supernova and disappears, all right? But this is the scheme here. I have the stats for each of the different stars, for G stars, K stars, some of the other ones, F stars, right? And so I have the stats for all of these things. I put them up on the board so that the students can look at and write down the information. And they keep in mind as I count down the timeline. So let's say we start off at the very beginning, at time 0. Here's the empty, or not empty, but it's basically a molecular cloud here. The molecular cloud starts to collapse down and form these hot spots where stars can form. And so I said, okay, well, what happens at the time, at the very beginning? Well, we have some of the blue hot stars showing up, all right? So they start showing up at the very beginning there. And then as time goes on, of course, we end up getting some of these other stars, the type B stars start showing up. And so I have a population of these things forming, inside the molecular cloud here. And as time goes on, of course, let's see if I write this down now somewhere. Here we go. So along the way here, roughly speaking, about 1 million years down the line, the type O stars, these things here, are no longer on the main sequence. They actually become red giant stars. And so I have these things representing the red giant stars. And so I replaced the deep blue ones with these things temporarily, just to indicate that they're there, and then they disappear. They blow themselves up or supernova or whatever. They become supergiant stars for a little bit and then they disappear, right? So we end up with this. And then as time goes on, of course, we have the type A stars showing up as well. From the molecular cloud, they come together and they turn on the nuclear fusion process. So they come in and they start shining, right, on the main sequence. So The thing is, though, I mean, every student has their beads to be mindful of. Each were given 2 beads to sort of like keep track of, and they were given the stat sheet. So I would be sitting there going, okay, it's now 100,000 years into, in the timeline, or 200,000, 300,000, 400,000, 500,000, 1 million, 2 million, 3 million, 4 million, 5 million, 10 million, right? 20 million. 25 million, and so on. We just sort of ramping up the timeline speed, right, as we go along. And this thing changes, right? Obviously, at some point, you get the G stars showing up in the population here. And these other stars that are these light blue ones, they start disappearing and become red giant stars. So we replace those with the red giant stars like this temporarily. All right, so these all become red giant stars over here as well. Like so, like that, and we indicate that they are fleeting. They don't stick around for long, right? Meanwhile, we have the G stars showing up and so on, right? So as time goes on, these things evolve, and it changes, right? These disappear over time, leaving behind, the lesser mass stars sort of continue on the process there. Now, this is just a simulation, all right? And of course, we're not taking into account the fact that as the other stars blow themselves up in a supernova event, the gases could actually recondense down into becoming other stars at that point. They're smaller or whatever. We don't talk about that. All we're doing is basically providing a simulation and a timeline associated with which stars show up first, how long do they stick around in the field of things here, and then when do they, go away, all right? Now, obviously, I also forgot to mention that these smaller stars, like the yellow hot stars here, when they die, they are followed by a red giant. And then, after the red giant phase, they get replaced by these things, right? These are the tiniest of the pom-poms. And I forgot to do this during class, but, as one of the red giants go away, it gets replaced with a white dwarf, okay? Little pom-pom there. So this simulation here lasted about maybe 20 minutes. And, we went through the whole process of going from time 0 all the way through using the different, stages or steps of time here that I wrote down on this paper. Going from 0 to 100,000 years, 200,000 years, and so on, all the way up to 1 trillion years. And so by the time we get to 1 trillion years, the type M stars, have shown up, and they are evolving at this point, in the process there. You end up at the very end here, 1 trillion years down the line, the stars are not going to be, G stars or anything in the middle there. They're all going to be kind of the reddish ones that are left behind. So you end up with a bunch of white dwarfs, a bunch of red dwarf stars, the type M stars, and a few, if there's any surviving things, of the red giants, which will ultimately become also white dwarfs or neutron stars or black holes as well. So, this scheme here is still, in the works. I'm still trying to refine this thing to get the numbers correct. I did an approximation of those things, of course, just very quickly before class. They're not as precise as they need to be, but, the students appreciate the fact that they're able to see this in real time, and their participation, their interaction of bringing these beads up, putting them down, swapping them out for the pom-poms, swapping them out for the little tiny pom-pom for the white dwarf, it helped them to visualize what is going on in an evolving star cluster. So, and in this way, we're able to also figure out by understanding, this time in, in the timeline here, how old the star system, the star cluster is, all right? So if it contained, at 100 billion, it contained a certain smattering of stars and red giants and white dwarfs, it would look something like this. So that would be indicative of that particular age for that star cluster. So that was the whole point, all right? I am hoping to refine this a little bit better. It was confusing. It took some doing for me to sort of like manage it all, okay? And get it all together. But hopefully over the next few iterations, over the next few semesters, I'll be able to at least, get it down to a little bit more streamlined, okay, in terms of the ability to change things out and such. But I did want the students to interact, and be a part of the simulation as well, which is why I had them tactily bring the beads to the fabric here, right? And this is all displayed on the camera here, right? Onto the big screen, so the other folks in class can actually see what is going on as well in the process, all right? And as I called out the timeline, where we're at, folks would come up, be on their toes, and change out these things as they needed to, right? So that was the whole point, all right, to help them sort of like connect with the timeline associated with a star cluster. That's it.